Deploying autonomous agents across an enterprise requires handling a massive volume of multi-turn interactions. For organizations managing sensitive code bases, the operational objective is clear. Shift these high-throughput workflows away from closed-source foundation models and onto private, local small language models, like Qwen 3.59b. Relying exclusively on massive, remote models like GPT-5 or Claude Opus to power continuous agent loops creates severe operational bottlenecks. The API token costs scale unsustainably, latency spikes stall execution, and strict enterprise data privacy limitations often forbid sending proprietary data to external servers entirely. But moving to a compact local model introduces a catastrophic barrier. When human-authored or frontier-generated skills are transferred directly to a 9 billion parameter model, the agent experiences widespread task failure. This slide details the Skiller framework. Evaluating Qwen 3.59b on SWE Skills Bench, the baseline achieves only 26.2%. But by applying Skiller to refine instructions, that same 9b model jumps to 82.8%, outperforming closed-source systems like Monos. This performance leap proves that the deployment barrier for compact models is not a lack of inherent compute capacity. The failure stems from a structural model mismatch that requires shifting the focus of optimization from neural weights to the executable instructions themselves. The model mismatch bottleneck occurs because standard skill libraries are written with implicit cognitive assumptions. Human engineers author procedural instructions expecting the executing agent to possess deep implicit reasoning and the ability to dynamically recover from errors, capabilities native only to massive foundation models. When a compact model encounters these open-ended, multi-branch instructions, it struggles to infer the missing context. It will hallucinate command line parameter names, combine mutually exclusive execution flags, and skip essential verification steps, claiming a task is complete before output files are even written. The sharpest divergence happens during error recovery. If a frontier model encounters an unexpected traceback error, its extensive parameter capacity allows it to dynamically replan its approach. A small language model, lacking that reasoning depth, typically repeats the exact same invalid command, trapping itself in an infinite loop of unproductive queries. To push a 9b model past the 80, the optimization happens directly on the procedural skill artifact itself. Traditional reinforcement learning updates an agent's behavior by calculating policy gradients to adjust the underlying neural network. Skiller flips this architecture. Instead of updating the compact model, the frozen model is treated as a component of the environment. Returning to the architecture diagram, Step 1 establishes the compact model agent loop operating within Environment E. This environment encapsulates the target compact model, the tool workspace, including the terminal, file system, and interpreter, and the official task verifier. Conditioned on an initial, generic skill document, the compact model attempts a task instance. It performs a multi-turn rollout, generating a complete trajectory of observations and actions within the workspace. The environment evaluates the resulting artifacts against ground truth unit tests. It returns a scalar reward and detailed error diagnostics, which form the basis of the optimization state in Step 2. This state tuple aggregates the interaction data, directly pairing the small model's failing trajectory with a golden reference trajectory generated by an expert agent. All of this is logged in a replay memory. Storing historical failure signatures ensures the optimization loop explores bounded variations and avoids cyclic regressions. In standard reinforcement learning setups, the state is represented as a numerical matrix. By formatting the state in natural language, the system preserves rich, qualitative context about exactly why a specific tool call failed. Pairing these structural failures with expert examples in plain text creates a high-resolution map of the exact moments the small model deviates from the correct path. That high-resolution map is fed into the framework's analytical engine, the natural language critic. It performs a causal differential analysis, tracing downstream test failures back to their earliest causal source, like an unverified file path corrupting output data. Rather than approximating a continuous scalar value function, this critic translates its diagnostic analysis into discrete, concrete modification suggestions, or hallucination. The actor also synthesizes standalone, deterministic helper scripts to handle complex, multi-step logic. Step 5 applies the delta to the existing procedure, outputting the refined skill artifact. This entire iteration loop executes strictly in structured text. No neural network weights are updated, avoiding catastrophic forgetting. Because the actor receives precise, verbalized feedback detailing exactly which parameters must be constrained, the policy stabilizes rapidly, converging in drastically fewer environment interactions. The Skiller architecture functions as a technical compiler. It takes abstract instructions designed for senior reasoning engines and translates them into rigid operative templates that small models require to succeed. The refinement of these skill templates follows a strict four-stage specialization lifecycle. Starting from a generic outline, the critic and actor first establish Step 1, input grounding. This injects explicit commands to verify file paths and data types. Then the iteration moves to Step 2, task local helper injection. When an agent is tasked with multi-step procedural logic, like AST parsing or nested regex replacements, standard instructions describe the operation in prose. Forcing a compact model to invent ad hoc scripts to execute that prose invariably induces syntax errors, index overflows, and complete context derailment. Skiller resolves this by offloading the computational complexity. The actor writes and verifies a standalone, deterministic Python script that encapsulates the data transformations, saving it directly within the skill directory. The instructions are simplified into a single CLI invocation. The model's responsibility is reduced to executing the pre-written helper script and checking the exit code. In the final iterations, Step 3 embeds explicit assertion blocks and fallback routines into the skill. The model must validate that all output files conform strictly to the required schema before finalizing the task. By separating high-level control flow from low-level mechanical computation, these helper scripts shorten the agent's interactive trajectories by up to 60%. Shorter trajectories minimize context accumulation and eliminate the compounding error loops that derail small models in long-horizon tasks. This structured lifecycle takes a fragile generalist model and equips it with the specific, bounded tools required to execute as a highly reliable specialist agent. The jump to 82.8% on the software engineering benchmarks is driven directly by this shift, translating ambiguous prose instructions into deterministic, executable code tools. This targeted behavioral alignment reduces token consumption while maintaining execution reliability. Methods like SkillX that rely on unconstrained textual generation for failure reflection incur significant prompt inflation and higher generation latency. This chart compares the token economics of both methods. Generating specialized skills using Skiller's causal diagnostic loop costs $8.95 per task, compared to $14.55 for SkillX, a 38.5% reduction in API expenses. Because the Actor-Critic isolates the precise causal failure point rather than generating generalized reflections, the actor produces surgical edits. It generates only 0.15 million output tokens during the optimization process, compared to SkillX's 0.37 million. And despite utilizing drastically fewer generation tokens, those surgical edits yield an average accuracy increase of over 10 percentage points across all major benchmark families. Looking at the final results, the return on investment is clear. Taking a 9 billion parameter model from a 26.2% success rate to 82.8% for under $9 validates the mathematical efficiency of this optimization pipeline. This unlocks the widespread deployment of private, local agents. By enabling ultra-compact models to execute complex software engineering workflows with high reliability, organizations can bypass closed API dependencies entirely, running powerful autonomous systems on consumer-grade hardware. It represents a structural shift in how we approach agentic alignment. Compiling operating instructions into deterministic subroutines provides the rigidity small models need to execute without the ambiguity of open-ended prompts. Successful on-premise automation relies on mathematically refining natural language policies into precise, executable toolsets. This allows compact agents to succeed without the overhead of increasing parameter counts.